All right, so good morning, everyone. Thanks for tuning in. Today, we're very excited to have Professor Andras Vasy. He's going to tell us about the Feynman propagator and self-adjointness. So please take it away.
Thank you very much, Jim, for the kind introduction. So, for a while we were all giving Zoom talks, and very much used to it. But so I've gotten unused to it in the year past. So we'll see how this goes. And so part of it is that usually when I give live talks, I give board talks. So corresponding, as I just mentioned to Dan, this was a last-minute revision last night. So hopefully there aren't serious issues in the way I organize things, but we shall see. So anyway, what I'm going to talk about is the Feynman propagator and self-adjointness for the wave operator or similar things. And so various parts of this various aspects of this talk are joined with Viet Dang, Jesse Geredman, Nick Haber, and Michael Rochna. So let's get started with a bit of a reminder. So in the wave equation, right? So let me just recall the wave equation. So we have a Lorentzian spacetime. So M is our underlying manifold, G is our Lorentzian metric, and box G is my wave operator. And just for definiteness, I'm going to take it to be signature 1 and -1, so the mostly negative convention. And so usually for wave equations, when you say a PDE person, one thinks of Cauchy problems for whatever reasons, going back probably at least to the 18th century, so before Cauchy. And so here you take an initial surface, hypersurface S, and you specify the unknown function u that you're trying to solve for and its normal derivative at S. And then one has, first of all, a unique local solution, and under a global assumption, so this is global hyperbolicity, so basically says there's a global time function and S is a level set. I mean, there are different ways of phrasing this. There's a unique global solution. So that sounds nice and simple. So now for various purposes, or maybe I should say that, there are an awful lot of slides on the very top, so it may look scary. So my plan is not to get through the whole thing. I will roughly I have a thank you slide about halfway through, but in case there are some questions, so don't worry about the lots of slides on top. Anyway, so the Cauchy problem is equivalent to an inhomogeneous problem. So you want to solve the equation box u equals f, where f is, say, supported in time bigger than some t0. And you want to find a u which is also supported in t bigger than t0. And the same thing for the less than or equal version, so t less than t0. And so the corresponding solution operators are the forward in time or retarded, and the backward in time or advanced solution operators. So, okay, so that's good. Now, one question that arises is, what are the natural inverses of box? So it turns out in reasonable settings, and I will discuss this in some various ways, there are two more natural inverses, the Feynman and the anti-Feynman propagators, so like introduced by Feynman in the Minkowski setting. But so these are much more global than either the advanced or the retarded solution operators. So even the local behavior of the solution depends on the global structure of the space-time. This dependence is via a smooth contribution. So, I mean, what I want to think about is elliptic PDE and Riemannian geometry, right? So if you're solving an elliptic equation, so say Laplacian u is equal to f with, say, some insane domain with there's some boundary condition the domain, the solution at some point in the middle of the domain will depend on what the right hand side is everywhere, and also if you have a boundary condition that's non-trivial, what that is everywhere. And this is the normal state of affairs, right? So if you think of solving solving an equation, it's like the analog is inverting a matrix, like you are inverting an operator, inverting a matrix. When you're inverting a matrix, you don't really expect that in order to find out what, say, a block of the inverse is, that's the analogous thing, you just take the corresponding block in the original matrix and invert it. So it's a bit abnormal what you can do for the wave equation for the advanced and retarded problems, though of course you can do it. So it's true, but you should think of it as unusual, and you shouldn't expect this to ever work. So sometimes it works, but the chances of this are zero in any reasonable measure, let's put it this way, when you pick random problems. Okay, so concretely, the nicest settings in which these global inverses exist are usually non-trapping, which what this says is that the non-geodesics or light-like geodesics, these possess a good structure. And so I'm not going to be I don't want to write too many precise statements, but so a good example would be what I call symbolic order 0 Lorentzian metrics on Euclidean space. I mean, Rn as a vector space. And so what this says is that when you differentiate your metric components, the more you differentiate, like alpha is the number of times it's a multi-index, like you do alpha 1, x1 derivatives, blah, 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 alpha n, xn derivatives. So the more you differentiate, the more decay you get. So this is a usual thing in Riemannian geometry, the asymptotically flat spacetime. So this is an analogous statement in Lorentzian geometry. And so these are like Minkowski metric or asymptotically Minkowski metric. And so this is the starting thing. This is what puts you into a category, like what kind of objects you are going to think about. And then because this is things happen. This is not an elliptic problem where things are just stationary. I mean, there's no time, nothing changes. Stuff moves around here, stuff propagates. This is wave equations. So you will need a good structure for the non-geodesic flow. So basically, this says is that at space-time infinity, so is best thought of as compactifying Rn, having a boundary at infinity, which would be a sphere at infinity, corresponding to different directions of going out to infinity. There will be in phase space, so the cotangent space, but it's always phase space that matters here. In phase space, this non-geodesic flow, so the cotangent space, the Hamiltonian flow, will have a good structure, like a sourcing structure. And the usual, so in an asymptotic Minkowski case, this would be the light cone at infinity, or more precisely, it would be its conormal bundle in the appropriate sense. Okay, so that's sort of
does this non-trapping condition exclude like black holes with photon rings and that sort of thing? Or?
That's right. So at this point, this would there are some. I'm trying to be in the simplest possible situation right now. So this is not necessarily not a critical feature, but certainly this is when things go the easiest way for me to explain. And these are the things that have actually been written down. That's another important fact. So yeah, but it's a good question. So one question is, how do you encode these inverses? So one way to encode this, which is a nice way for an analyst, and I should say that I'm no way a functional analyst, and I used to think, coming from more elliptic problems, that all these function analysis considerations are overblown, but in fact they're super nice in this setting. So the way you can encode the inverses is that you think of you let the wave operator act on different function spaces. So different inverses will correspond to different function spaces. Okay, so concretely, these function spaces will be Sobolev spaces, so derivatives in L2, and in fact they will be weighted Sobolev spaces. So there are two orders. So an S and an R. So S is, say, the differential order. How many derivatives you have? Well, not in L2 because there's this weight. So it would be a weighted L2 space, and the weight is a polynomial weight. Like at infinity, it would be like norm x to the power minus r. So x to the power r times the function u should be in L2. That's what it would correspond to. And what will happen is that actually for this, one of the orders will be actually not just a number, but will be a function. And so it will be a function of the phase space, the cotangent space, and this is going to be monotone along the Hamilton flow. So namely along the lifted non-geodesics, so the non-geodesics in phase space, and will satisfy certain conditions. So now, so I said Sobolev space, but the Sobolev space you use actually depends on the problem. So in particular, there's a difference between the actual wave operator and its spectral family, so box minus lambda. So most of what I will say is about box minus lambda. So box is the analog of the Laplacian, right? So Laplacian is a flat space-time. That will use a different functions, different Sobolev space. So the subscript B is denoting this. And the key feature of this is that, so this is Melrose's B Sobolev space. So here what this means, and this is very common in the Riemannian world, so like people working on constraint equations, say, things like that. So the regularity, so differential order, is measured with respect to linear vector fields like xi, dd, xj. And the weights are, again, powers of just norm x. So these are for example, having being in H2 with, say, r equals 0, HB 2, 0, would say that you can take any two factors of an xi dd xj, like an xi1 dxj1, xi2 dxj2, apply to you and get things in L2, as well as if you just take one factor or 0 factors. So that's what this space would be, but more typically will be think about the spectral family. So we have a lambda, so lambda times identity, if you want, which is typically going to be non-zero. And so in this case, the spaces will be standard Sobolev spaces. If you are Euclidean space, standard weighted Sobolev spaces. So the standard derivatives, there's ddxi, and the weights are still powers of norm x. Now, so the difference between these two, if you want, at like a phase space level, like what are these derivatives quantization of, is that you use a different frequency variable. And so at the phase space level, what you are think about is, for example, what's high frequency? High frequency is a different thing when you change your Sobolev space. It means something different. So frequency is not with respect to any particular metric in this case, like it's not with respect to the actual Minkowski-like or whatever metric. It really comes from the underlying operator algebra. So the way you should think about it is that, right, how is the world ordered when you think about geometric things? The number one thing is the manifold structures, a smooth manifold. And that's what you first should think about. So that sets up the analytic category that you want to work on. And then the number two thing that's very secondary, but of course important for actual problems, is an actual metric you'd want to work with. But for example, if you're in Riemannian geometry and in a compact manifold, one metric is as good as another metric in terms of the underlying operator algebra structure or Sobolev spaces. All Sobolev spaces in a compact manifold do not care about the compact manifold, do not care about the choice of a metric. So it's irrelevant. So okay. So now the other thing that this slide said that I should reiterate is that one of these two orders will be a function on the phase space. So in this lambda not equal 0, it's going to be the decay order that's actually variable. In the previous case, it's the differential order that's variable, and it corresponds to the different frequency scaling that these two spaces use. Okay, and so basically the reason why the lambda equals 0 case is different is because you have to use a renormalization, because otherwise this is right. So the problem with a wave operator without any spectral parameter added is that what does it look like? About the leading order, it looks like the geometric function, right? So we're going to discuss this in a little bit. And the geometric function, so the square norm, quote unquote, of in this Lorentzian setting of a covector. And unfortunately, a square of something vanishes quadratically at the 0 section. So it's a degenerate problem. And so you renormalize it. But I won't really get into this. Okay. So now but you can just think of everything here so far as a sort of black box. And so what will happen is if you now think of box minus lambda, then under suitable global assumptions, so this is this non-trapping, for instance, there are still 4 choices with respect to which this box is Fredholm. So Fredholm means so basically invertible up to finite rank abstraction. So closed range, a finite codimension, and finite dimensional kernel. And in fact, the Feynman, the anti-Feynman choices are always invertible. So positive lambda with my signs is positive squared mass. Negative lambda is negative squared mass in the Klein-Gordon normalization. And in a moment, I will also do lambda complex. So what happens is that you will think of this this box minus lambda as a map from one space, which is sort of like a Sobolev weighted Sobolev space, modulo that the order is really a function, to another with an extra thing added, to another space which is actually again a Sobolev space. And the slight funny thing of the domain is that it has an extra condition built in. And moreover, this variable order R will have to satisfy appropriate inequalities, and these inequalities are the things that choose which inverse you are taking, so or which inverse you are trying to construct, which Fredholm problem you're constructing. So I will explain it more concretely in a little bit. But so again, the choices you make, so the differential order here actually doesn't matter because will not play a role at this sort of source sinks. So differential order S actually makes absolutely no, I mean, you have to choose something to get the problem, but it doesn't matter what you pick. It's sort of like an elliptic problem, even though it's not elliptic, but the decay order makes a difference. And that's what you pick to pick out a particular inverse or almost inverse of this operator. So that's the setup for real lambdas, and for non-real lambdas. So they're also interesting because you are trying to do, if you're trying to think about self-adjointness, so when you have a symmetric operator, self-adjointness is more or less a statement about what the operator minus plus or minus I does in terms of, for example, having a dense range in L2 on some a priori defined smaller domain. So essential self-adjointness. So so we also care about non-real spectral parameters, and then the statement is that what problem is well behaved. So we had these 4 problems just from for say positive lambda, the retarded, advanced, the Feynman, and the anti-Feynman. But of all these 4 things, only one will be well behaved, either the Feynman or the anti-Feynman, depending on the sign of the imaginary part of the spectral parameter. But for that one is actually well behaved. And moreover, if you take limits for either this, so either the Feynman or the anti-Feynman, as you let the imaginary part go to 0, you will get the resulting inverses of box minus lambda, where lambda is real, namely the Feynman and the anti-Feynman inverses. So when you do the like the usual sort of resolve and you do an inversion away from the reals and take a limit to the reals, you will get the I mean, as one would reasonably expect, exactly the Feynman and the anti-Feynman inverses. So in particular, you are really inverting the operator, even when, so you think that, well, the reals are the spectrum of the wave operator. That's so wave operator minus lambda is not invertible. That's not a true statement. But the true statement, it's not invertible if you're trying to think about it as a map basically into L2 from an appropriate space. But that just says that these are the wrong spaces to try to do the inversion. It's not a statement about the wave operator. It's a statement about having picked the wrong spaces. Why might one pick the wrong spaces? Maybe because one cares so much about self-adjointness. That doesn't mean it's the right choice. It's one's own problem. All right. So nonetheless, this is all related to the essential self-adjointness, which, as I said, is basically a regularity statement for these inverses, which are now well defined as the Feynman and anti-Feynman inverses, depending on the sign. And so what you really want is that they both map some dense subspace, such as complex supported C infinity functions, to a suitable subspace of L2. And so what's not clear, just because you know how the these Feynman spaces are constructed, this is XXR is the domain for the wave operator, and this Y is the target. So when you're inverting, you're getting up to XSR. So there are limitations on what R is, as I mentioned. So this is the variable order that has to satisfy inequalities, and this may not allow you to be in L2 directly in the way I set it up. And I had a paper a few years ago in which concretely this was the domain that I chose. It's a slightly funny looking space. And actually, maybe I'm going to not really so much go into this, but I want to say that there's actually a more natural way of doing it. I realized much more recently, like months ago. We sort of a more complicated space with more indices, but you actually get a much nicer. Like the first one was, like this paper I'm quoting on top, which says that the wave operator is essentially self-adjoint with domain complex ported C infinity functions. So that had a rather ad hoc sort of borderline argument. In fact, there's a much nicer way of doing it, but maybe I'm going to ignore it. I just want to emphasize that it is actually essentially self-adjoint. Okay, so given this, maybe I've skipped the top part, but given this essential self-adjointness, it's then not surprising that actually the difference of the extreme propagator differences, so the by the extreme I mean the Feynman and the anti-Feynman, and extreme might make sense a little bit more why I chose this word in a little bit. So if you take the difference and multiply by I, this is going to be non-negative. So that's something I actually proved earlier. So what this is the positivity of the spectral measure. So, once you have essential self-adjoint, this is automatic, but there are sort of less technical ways of seeing it, although now I can see the spectral, the essential self-adjoint is also in an easier way. Okay, so why is this good, this self-adjointness? Because one reason it's good is, for instance, it allows one to define by the functional calculus things like box minus I epsilon to the power minus alpha. And I mean, more generally, not just for this real part alpha bigger than over 2, but when you have this extra restriction real part alpha bigger than n over 2, then moreover, you can take the integral kernel, the Schwartz kernel of this operator, and restrict it to the diagonal. And what Viet-Dang and Michal Rochna showed, actually, I think it's been published since then, but they haven't updated the reference, showed that for even dimensions, this undiagonal restriction has a meromorphic extension to the complex plane with poles at certain places. And at n over 2 minus 1, the limit as epsilon goes to 0 of the residue is up to a constant factor, the scalar curvature of the Lorentzian metric G. And so they also computed the residue at other poles. And this is what it can be thought of as an analog of what Shamsuddin and Kuhn did in the Riemannian setting, what they call the spectral action principle. So spectral action because the Hilbert action has the scalar curvature in it, and the scalar curvature arises as a residue of this sort of functions of the Laplacian in their case, and now the wave operator in this more quote physical unquote case at certain places. And one thing that's sort of ongoing work of mine with Viet-Dang and Michal Rochna actually aims to extend this to the Dirac case. And so the main thing is that there's no self-adjointness anymore with respect to a positive definite inner product. But really, in terms of functional calculus, this is a very minor issue. You just kind of just quote things from a textbook. Instead, you just have to do things right. So, I mean, this is the sort of analytic part is actually done. It's various computations that are being currently carried out in this setting. Okay, so in fact, I wanted to step back and say that all this is not really specific for the wave equation, right? It's a general non-elliptic phenomenon. So, so in particular, one can think about ultra-hyperbolic PDEs. So this is where you have, if you want, in terms of space and time in the Lorentzian world, you would have a bunch of space and a bunch of time directions. So at least two of each. Otherwise, you could just switch what you call space and time. Or so more generally, the Laplace-Beltrami operator associated matrix of arbitrary non-Riemannian signature. And so the thing is that these operators actually very much like the wave operator. The only difference is that the Cauchy problem is terrible for them. So you will not have an analog of the Cauchy problem, but you should think of this as the fault of the Cauchy problem. It's not the fault of the operator. It's the fault of the person who is trying to impose a Cauchy problem for it. So it turns out the only inverses you would get normally, or Feynman problems, are the Feynman and the anti-Feynman ones, Fredholm problems, the Feynman and the anti-Feynman ones, and which work just as well. So you don't get the causal ones, the advanced and retarded, but well, so what? That's life. It's again not the fault of the operator. And I just want to give a bit of context for it. So I'm certainly not a QFT person overall. So I'm even a mathematical QFT person. So a lot of the motivation for why I did, so like the positivity things came from discussions that I had with Christian Gerard, and the self-adjointness issues with Dzerzhinsky, who had asked me about this earlier, and he had some partial results with his then student Simpson. And then in various other settings, since the self-adjointness has also been addressed by Shu Nakamura and student Koichi Taira in some other settings. And just comment that, right, so in this QFT setting, one is interested in the positive properties of various differences. A weaker version, so up to smoothing operators, follows from similar arguments, but the strict positivity statement does not follow in general. So, for example, if you take we have this well-defined Feynman inverse, you take one of the causal inverses, take the difference, while it's not going to be positive in general, like well, it was not really the difference you take. So what would you do is you would like 2-point function. So it's not really going to be positive, but it's going to be so up to smoothing terms. So I will get back to this in a moment, but I want to explain a bit of where these choices come from. So why can I say that there are 4, or in some cases fewer, sort of distinguished inverses, or at least almost inverses, so up to 5-dimensional obstacles. So maybe this is a good point to ask if there are questions so far. I know I've been going a bit fast.
Well, I guess I have a quick question. On the last slide, you said that I guess that there's like sort of a sensible propagator even when you have multiple time directions, which I guess was a little bit surprising to me. I would have thought things aren't necessarily determined later in time when you have an extra time-like direction. Do you have like an intuitive explanation?
Yeah, so in fact, that's what I will get to right away. So how these different choices come from. But basically what will happen is that, actually, let me just do that. Let me just go on and we will see exactly what happens. So it's a very good question, and it's about to come up. So in order to discuss this, I just want to recall so first I'm just going to think about like local behavior. So this is not going to be the full answer to things. That's going to come a bit later, but I have to say something about the local behavior first, because it's easier to say. So when you have a differential operator, so it's like a sum of derivatives with some coefficients up to some order, the principal symbol is just taking the leading order parts. And so when you think about local theory, so it's in compact subsets of your manifold, what you should think about this. So what is this principal symbol good for? It's good for capturing the behavior of the operator at high frequencies. So like geometric optics, that kind of thing. So, or analytically concrete, it's not an approximation, but up to compactness, it's exactly describing what's happening. So high frequencies means that norm xi goes to infinity. Here, norm is, you shouldn't think that it's a well-defined particular norm. Take local coordinate charts, it's your favorite, say the standard norm in each coordinate chart. Of course, they're not the same, but you say, who cares? They're equivalent. So you have to quotient always by irrelevant things. It's the key thing in most of mathematics, probably. Anyway, so we're thinking about what happens as xi goes to infinity. So in particular, the behavior at xi goes to 0 is totally irrelevant. You shouldn't even think. We are making this into a homogeneous polynomial because that's easier to think about than compactifying the space and adding an infinite xi equals infinity appropriately. Okay, so what's called the characteristic set of this operator is really energy shell. So just for this principal symbol, little p, is equal to 0. And so outside the characteristic set, the operator is elliptic. So just like the Laplacian. So they have very good estimates for it, which is what one loves as an analyst, and there are no propagation phenomena. So you should think that say you're in phase space now, right? So x comma xi. So say in the wave equation, it might look like P might look like, I don't know, xi n squared minus xi 1 squared, blah, 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 xi n minus 1 squared. So you would have this double light cone in the fibers of the cotangent bundle. You really should forget about the 0 section. It's irrelevant. In fact, any finite point is irrelevant. You really think about the limit as you go out to infinity, but let's just keep the finite points in because it helps with human frailty. Outside the light cone, which is almost everywhere. So if measure theory was the answer to all questions in the world, it will be done. Outside the light cone, this operator is elliptic. So it's just like the Laplacian. Its principal symbol doesn't vanish. Okay, so nothing is happening there. We understand perfectly well what's happening, which is nothing interesting. All right. So then we go to the characteristic set, so the energy shell. And so there what happens is that you can propagate estimates or equivalently singularities. So singularities is described by exactly high frequency behavior along the classical dynamics. So what's the classical dynamics? What you're going to do is you're going to take the integral curves of the Hamilton vector field of this principal symbol. So use the symplectic structure on phase space to turn this function p, or really its differential dp, into a vector field. So let me emphasize that this is this is the Hamiltonian perspective. But let me emphasize this is the space-time Hamiltonian perspective. So this is the Hamilton vector field of the space-time Hamiltonian. Its symbol turned into a vector field. So going back, the statement is that you can propagate estimates along the integral curves of this vector field. And so in the mathematical quantum field theory, this had an impact due to so Duistermatt and Hermander in the early 70s to discuss this. And then Radzikovsky, in part because of Whiteman's questions, exactly with QFT, which is like positivity-related questions. And then Radzikovsky used this, I think I will comment on this later, used this for as a replacement for the usual Adamar condition. So, so concretely, what Duistermatt and Hermander did was they constructed parametrices. So these are approximate inverses for operators which are non-elliptic. The Hamilton vector field is not radial, so it's not the multiple of sum of psi j dd psi j anywhere. So this is the dilation orbits, right? The psi dd psi is the dilation vector for the generator of dilations in the fibers of the cotangent bundle. And so the parametrices, these are approximate inverses up to smoothing operators. So operators with a smooth C infinity Schwartz kernel. And what they did concretely is that they used the machinery that they just developed, or Hermander mostly developed, the machinery of Fourier integral operators, to reduce a general operator like this locally to a model case, which is just a standard derivative with respect to one, whatever direction, say xn. And this in particular gives a proof of propagation singularities, that you can propagate estimates equivalent to singularities or regularity along integral curves of HP. Now they also showed, so this is the top part is what's mostly quoted from their work, but they also showed in the same paper that if the characteristic set, so the energy shell, has k connected components, and so k would be 2 for the in the Lorentzian case when the underlying when there's a time orientation and the underlying manifold is connected. So namely in each so if the k connected components, there are 2 to the k distinguished parametrices. And so what happens in each component of the connected component of the characteristic set, energy shell, you get to decide whether you solve away singularities or propagate estimates forward or backward along the Hamilton flow. And you can instead phrase this in terms of wavefront set of the Schwartz kernel of the parametrics instead. So so this now gets back to your question about the ultra-hyperbolic problems. So what will happen in that case is that the characteristic set will just have one connected component. And so what you get decide whether am I going to go forward along the Hamilton flow or going backward along the Hamilton flow. But there's no underlying time variable on the underlying manifold that corresponds to anything. So that's why the Cauchy problem is terrible. But correspondingly, the conclusion is not that the operator is terrible, but one should not do the Cauchy problem. So in general, there are 2 extreme cases. So we have a bunch of connected components. And so this is this is why I call the extreme propagators. And there are the 2 rational things that independently minded person would do. Namely, either in each component of the characteristic set, you propagate estimates forwards or regularity forwards, that is, say, singularity backwards, or you do it the other way around. So in each component, you propagate the estimates backwards. So these are the Feynman and the anti-Feynman parametrices for Duistermatt and Hermander. And so, so this is where Whiteman comes in. So answering a question of Whiteman, they also showed that you can actually choose these distinguished parametrices, so there are 2 to the k in general, so that I times their difference from the Feynman propagator is positive. So this positivity is important for quantum field theory purposes. So the 2-point functions are essentially such differences, and so they should be positive for basic QFT constructions. And then what Radzikovsky did, so as I said, the 2-point function before, this 2-point functions positive is important. So that's like differences relative to the extreme. So the Feynman or the anti-Feynman with an appropriate sign that should have a sign itself up to an I. So, and then Radzikovsky actually used this Duistermatt-Hermander work to then explain microlocally. So in phase space, the Adamart conditions that's usually used in QFT, certain expansions at the characteristic set or the light cone, you turn this into a phase space statement. So that's microlocal, just phase space. That's all it means. In the for the wave operator, what will happen is that there are 2 connected components because it's double light cone, and so there are 4 distinguished parametrices, Duistermatt and Hermander, up to smoothing terms. Again, they are not actually inverses; they are parametrices in their setting. The retarded, the advanced, the Feynman, and the anti-Feynman. And so all this is up to smoothing. So there's quite a bit of freedom in the choices, and that's for limiting it. Duistermatt and Hermander also stated that they do not see how to fix this indetermination. Now, in order to do so, actually, we need to work globally. So we need to actually have an operator that we can invert. So inversion really means that you should have function spaces, the operator maps from one to the other, and then you're trying to ask about its inverse. All right. So for these global considerations, and so this is the last block that I will probably get through. So for these global considerations, a choice of how to measure frequency, which you can understand also as a choice of a pseudo-differential operator algebra at infinity, makes a big difference. And so for the for example, in what I sort of emphasized, which was the non-zero spectral parameter, this is what would be called narrows the scattering algebra that actually is origins in the work of Parenti and Shubin in the 70s in a non-geometric setting. But if you think of Rn, it's non-geometric, so Parenti and Shubin apply. So here, what you should think that if you take a differential operator like I wrote above, you should actually start first considering the full amplitude. So don't drop the lower order terms in terms of derivatives. So you can drop them locally. So when you're working in compact set, but globally you can't. And what you want to think, this is actually not a well-defined object as I wrote it down. So if you have a real manifold, the lower order terms are not well defined. But what happens is that at infinity, so really the best way to encode this is you compactify and then really at the boundary of the compactification. But you can also simply say that you will quotient out by appropriate things that you regard as equivalent. So basically having one order of decay at infinity. So at infinity, this is actually well defined. And so you really need this full symbols. You should not locally, your compact sets you can drop, and you should drop all order terms. They're not well defined. But at infinity, you should not. They're well defined up to the extent that they matter. Actually, this is also common in real life, that things are well defined to the extent to which they matter. And one shouldn't try to define them beyond that, even if sometimes one can succeed, but this is a distraction. So anyway, so for example, if you take just the straight Laplacian, so standard positive Riemannian geometry thing, Laplacian minus a spectral parameter. In the usual principal symbol sense, the spectral parameter is negligible. But in the full symbol case, this is not the case. The point is that, okay, psi squared, if you let, take x comma psi, say fix psi, but let x goes to infinity, well, this is independent of x, it doesn't change. So psi squared doesn't decay, but neither does lambda. They're exactly the same size. So a reflection of this is that there are things like plane waves, this e to the I square root lambda omega dot x, which are in the distributional, say temporal distributional null space of the operator. And there's an awful lot of plane waves, so it's not going to have something like a finite dimensional null space, and this would correspond to the or kernel, which this would correspond to the operator not being Fredholm. So it's a failure of ellipticity in a full sense. So ellipticity in a full sense is something that, including at infinity in terms of decay, should tell you that you actually have a Fredholm theory, but it's not. For the wave operator, okay, here's again, let's just take the standard Minkowski wave operator. Here's the analogous expression. So it's like psi squared minus the remaining psi squared minus lambda. So again, in the standard principal symbol sense, this lambda is negligible, but in the full principal symbol sense, it's not. So in particular, this means that if you take a non-real lambda, there's no characteristic set, right? This p cannot vanish if lambda is finite size, if lambda is non-real. And moreover, you also notice that if lambda is real, then depending on the sign of lambda, you have either one or two connected components. So there's two if lambda is positive and one if lambda is negative. Because this is a different, you pick out different hyperboloids. So you either pick out this sort of hyperboloid or this two-sheeted hyperboloid, one sheeted or two-sheeted. And again, finite size now matter. They don't matter in any compact set, but they matter completely at infinity. And infinity is not far away. So the saying of Merow's, infinity is closer than you think. It is much closer than you think. You really have to worry about it. And so, okay, and so this reflects why I said that for positive lambda, there are 4 Fredholm problems, or for the Feynman, anti-Feynman, the 2 causal ones. But for lambda negative, there are just 2, the Feynman and the anti-Feynman, that comes from this 2 to the number of characteristic set components. So actually, maybe here it's also good to point out, so why, one would say that, well, no matter what this lambda is, I can always solve a Cauchy problem, Okay, that's true, but you should keep in mind that that you cannot do it when you work in tempered distributions. So here the world is the world of tempered distributions, so distributions that, roughly speaking, grow polynomially at infinity. And so typically what you expect when you solve the Cauchy problem is exponentially growing solutions. So if you work in a subspace of tempered distributions, then those just don't exist. So you cannot solve the Cauchy problem in this sense. So it's the tempered distributions that pick out a preference for the Feynman and the anti-Feynman problems versus, or I should say, when lambda is non-real, versus the causal ones. And so what will happen is if lambda is real and say non-zero, then there are radial points where in this setting, radial points. So beforehand, when I talked about the Hermander, I said it was under the assumption that the Hamilton vector field is nowhere radius, not the multiple xi dot dd xi. Here, the analogous thing, because you're at infinity, being radial is x dot ddx. And there are points in the energy shell where xi dot ddx is actually, I mean, the Hamilton vector field is a multiple of x dot ddx at finite frequencies. And so what happens is, so the analytic theorem, like what you can do to prove estimates, is that there's a threshold regularity, and which would be like -1/2 decay, so weight -1/2 in polynomial weight. So what you would need to get so right, propagation is that things go from somewhere to somewhere. So you start your estimate, proving an estimate somewhere, and you keep propagating this. In order to actually be able to get started, you have to be, you will be able to start this at these radial sets, which are like sources or sinks for the Hamilton flow. They're sources or sinks if you compactify your space, as you should. And at the sources or sinks, you would, in order to start propagating, you would need to be in a higher regularity than threshold regularity space. And where you end up, you would have to be at a lower regularity than threshold regularity. And this, if ours are the same number, so in this case it's -1/2, this is what requires the decay order to be variable, which is variable order Sobolev spaces go back to Unterberger and Duistermatt in the early 70s. So this is why you need it, because there is threshold requirements. And so what you do, so how do you choose now between the different propagators? What you will decide is, so your Hamilton flow will have this global source sink structure. There's some sources and sinks for the flow in each component of the characteristic set. So they're going to be at the light cone at infinity, corner band of the light cone at infinity. And what you decide is, in each component, you decide, am I going to propagate my estimates forward along the Hamilton flow or backwards along the Hamilton flow? In other words, I'm going to decide, am I going to have in each component separately, am I going to have high regularity at the sources or at the sinks? And the other one, I will have to have low regularity, because to get a Fredholm theory, I will need an estimate for the adjoint as well on dual spaces. And so that's why really have low at one end, high at the other end. So I get to the global analysis picture in just 1 second. But that's the basic sort of the geometry part of what happens. Questions on this so far? Okay, so let's just discuss the sort of Fredholm aspect. So the statement is that in these real lambdas, in the settings I considered, there are k-connected components. There are 2 to the k natural Fredholm problems, and moreover, the extreme propagator differences are positive up to a factor of I. And if lambda is not real, and so again, this is the lambda equals 0 is joint work with Garrelman and Haber. And if lambda is complex, then there's actually preferred direction of propagation. That's why for lambda non-real, you only got either the Feynman or the anti-Feynman inverse in order to match with the elliptic estimate. So the operator was now elliptic at finite frequencies. And in order to have sort of matching behavior, in the estimate, so that you can have a Fredholm theory, it picks out which one you're doing, the Feynman or the anti-Feynman. As I already recorded, so Fredholm is invertibility up to fine dimensional obstacles, so closed range, fine dimension of null space and co-kernel between appropriate spaces. And typically these are essentially spaces that essentially some sort of weighted Sobolev spaces. And the generalized inverses or inverses correspond to the Duister-Hermann parametrices. But unlike in their case, because if you're working locally, you can only see things up to smooth errors. You fix things. And if you're in compact manifold, smooth is good, because up to smooth errors is pretty good, because you essentially do something up to compact errors. But if you're in a non-compact manifold, up to smooth is, infinity is big from this perspective. So it's a very weak statement. There are an awful lot of smooth errors. So it's a very non-compact error statement. And so and so recall that the Fredholm properties are usually proved by Fredholm estimates. So you show that U is controlled by PU up to an error, and similar V is controlled by P star V up to an error. And the key point is that this error is supposed to be weak, which is measured by the compactness of the inclusion of say X into Z1, and similarly for Y star into Z2. And so yes, for the adjoint, you have to have the estimates on the dual spaces, as I mentioned. So there's no freedom there if you want to get Fredholm theory. Like solvability, like the general solvability method we have in PDEs is using dualization. So this is the surjectivity or almost surjectivity part. Okay, and so let me just make this concrete to finish off. So in the simplest example of this sort of setup is for elliptic operators, say the Laplacian or Dirac operators in Riemannian signature on compact manifolds without boundary. And so there you would have an elliptic differential operator or differential operator. Ellipticity is that the principal symbols, that's the highest order terms, are invertible, so non-zero in the scalar case, but maybe you are working in a non-scalar case. All it means is invertible. The spaces X and Y would just be straight Sobolev spaces. And the Fredholm property follows from the elliptic estimate for either P or P star. So, I mean, one half for P, the other one for P star. So that's to say that you can estimate something in a Sobolev space HR in terms of the operator applied to phi in an M order weaker space. So this is elliptic regularity, basically. And the choice of the spaces are, like the orders is totally irrelevant here. This is why one thinks in sort of elliptic theory that function analysis is not doing too much from like local, compact manifold without boundary elliptic theory. So for these non-elliptic problems, though, for non-zero lambda, the elliptic estimates are replaced by these weaker estimates, where so the difference is that now you added a decay order because you are working in a non-compact case. So that's one difference. A more serious difference, perhaps, is that rather than going from S to S minus M and R to R minus L, so L is going to be the decay order operator, so it's 0 for the box minus lambda. So rather than just going from S to S minus M, etc., I went to from S to S minus M plus 1. So there's a loss of one derivative that's usual for like propagation estimates. Sorry. Go back. And so you have a similar thing for the adjoint. And so altogether, put together, but again, R and R prime need to have satisfied some inequalities, these threshold inequalities at the sources and sink. And so altogether, this says that the operator will be Fredholm on these sort of spaces. That's then would complete the discussion of how you get this 2 to the k in the general setting Fredholm problems. So thank you very much for your attention.
Okay, let's all thank Andras for a great talk. And we have plenty of time for questions. So if anybody has one, just unmute yourself and go ahead. I guess maybe I'll get started since I'm sort of a physicist interested in black holes. Could you just maybe elaborate a little bit, sort of what changes when you have trapping phenomena? Is it just that the characteristic sets are more complicated, or is there something sort of?
So yeah, so the issue is the Hamilton flow has a more complicated structure, and so what that means is that so because of the trapping, right? So the trapped set would be closed under the Hamilton flow, and so what you would really like to do is to propagate your estimates from where you want to start. So say some sources in this case to some things, but maybe in the middle there's this trapped set. So if you happen to be on the stable manifold of the trapped set, you will just asymptote there, and then you will never get out, and you in particular will not be able to go towards your sink. Say if you're trying to go from a source to a sink. Now, there are corresponding estimates at trapped sets that are more delicate than what I discussed, and this is actually key. For example, in like the proof by Peter Hintz and myself of the stability of slowly rotating Curtis-Ritter black holes. But they are weaker estimates, so you have to work, and this hasn't been. So I thought about this a while ago, but I never actually wrote it up properly. But for various reasons, I think I will do this soon with one of my students. So because the estimates are weaker, so they will be weaker, like what appears on top, they will have to be weakened. So like the P is measured in space S minus M plus 1, maybe it will have to be measured in a stronger space, actually, definitely. We have to measure in a stronger space. Now, the main way, so the estimate is actually fine then, so that actually is proved, but the main thing that you have to be careful about is that I just wrote down the space X on the bottom. And this is a perfect good Hilbert space, regardless of anything. You change the 1 into 2s, so what? Who cares? But an issue that you have to be careful about, and you have to discuss exactly what you want, is that you want this to be a good space. So you want something like compactly supported C infinity functions to be dense in it, right? So you don't want to like detach from reality. You want some good things to be dense in it. And for that, directly, the limitation is exactly this one. So right, so this P is an operator of order M comma L. So in principle, it maps HSR to HS minus M R minus L. And so putting this condition on PU is, could be quite tough. And if you want to be, if you want to see whether some space like complex supported C infinity functions are dense in it, you would do a regularization argument. And the point is that actually directly, so this is why you have to be more careful if you lose more, that directly only allows you one order loss relative to the a priori continuity, like what elliptic theory would correspond to estimates. So this S minus M R minus L. Basically, the one order comes from that the commutator of two operators is one order better than the product, that hence the one. So you have to go, because of that, you have to be more careful in how you phrase this. But so the estimates exist, but you have to be more careful in how you put this into a Fredholm theory.
Okay, thank you. Do we have any other questions? All right, well, I know a couple of us have to run at noon, so let's all thank Professor Vasy again for a great talk. Appreciated it.
Thank you very much for having me. It was very nice. I hope that I will be able to go at some point in person, but
yes, that
really
would be
busy
great.
anyway for me, so I wouldn't have been able to do it now for sure.
Yeah, hopefully things slow down for you. All right, thank you again. Appreciate it.
Thank you.